Now in this video we want to come back and talk a little bit about the idea associated with this effective penetration depth. You know, the data points in this display window here are plotted at what is referred to at their effective penetration depth. And notice that these numbers differ a little bit from the 1.5 times values of the intercrawl spacing that are usually used as the kind of the rule of thumb estimate for the penetration depth. So we'd have 1.5, 15, 30, and 60 meters. But instead over here in the IX1D plot, we have 4.7, 12.6, 25.5, and so on. Of course, remember these depths are not associated with any actual depth in our model, and that is easily shown over here just by comparing the behavior of the data, the location of the individual data points, with the depths in the model. We have two interfaces in the model, one at 10 meters, one at 30 meters, and we really, we don't, it's just, there's not a one-to-one correspondence between these two. But as we did mention before, you can see that, just if we didn't have this window over here, you can see that the terrain conductivity values start off higher, both in the horizontal dipole and the vertical dipole observations, and then they drop as the intercoil spacing increases. So that's maybe the limit of what we can get. We can get some relative sense for, okay, the conductivity up here in the upper layer is probably around 10, 20, 30, 40, 50 millisiemens per meter, and then it drops off to somewhere in the vicinity of 15 to 25. In fact, about 15. So that's general information that we can get from the apparent resistivity plot. Again, the assumption is that we're collecting data in areas where this assumption of a low induction number is valid. And of course, with these kinds of apparent conductivities, you can see that it is, because as we discussed before, this low induction number assumption usually starts to fall apart when the ground conductivities get above 100 millisiemens per meter. So we're well within the appropriate operating range for the EM31 and the EM34. The question here is, what are these effective penetration depths? Where do they come from? And where they come from is a little bit different than, well, we're going to come back to this relationship here of 1 over E. Remember, the skin depth is the depth at which the signal strength drops off to 1 over E, or 0.368 of its source amplitude. We talked about that earlier on in terms of, this is what the skin depth is. When the amplitude of the signal drops off to about, a third of its value at the source, that's the skin depth. Now, for these exploration depths, we're working with the relative response function. We spent a good bit of time talking about the relative response function. And we're still using this 1 over E, but in this case, this is the depth, or the normalized depth. Remember, Z is the depth, meters, feet, whatever, divided by the intercoil spacing. Of course, these two numbers have to be units consistent, because it's a dimensionless or a unitless number. But when the remaining area under the curve drops to 36.7% of the total area under the curve, that depth is referred to as the exploration depth. That 36.7 or 36.8% is approximately 1 over E times 100. So all these numbers that you see, in this case the 4.7, if we come back to this plot here, we have 4.7 here for the vertical dipole for the EM31 with the 3.67 meter interquartal spacing. That depth of 4.7 meters comes from this idea here, where we're working with the relative response function. So that hopefully gives you a little bit better feel for where those numbers come from. Again, you have to remember that these these interquartal spacings of 3.67, 10, 20, and 40 meters are associated with effective penetration depths. You should keep in mind that those effective penetration depths, these depths here really don't correlate directly with what we see over here in the in the model. Another thing to keep in mind is that even though this is 37% of the total area under the relative response function, that the apparent conductivity that we see, the contribution to the apparent conductivity we see from layers beneath this depth can account for much more than 37% of the apparent conductivity. So that's something else to keep in mind. Okay, we're going to be talking about a problem. We're going to be using IX1D to evaluate a problem. This is the background on the problem. We've got a wastewater lagoon over here. We've got a community that's down the hydraulic gradient from this lagoon. There's some concern that there is leakage and contamination of the groundwater that they're using for their homes. And the question is it contaminated or not? Can we determine that using a terrain conductivity survey? There is a well that gives us some control, and from the well we see that we have a layer of near surface clay which is about 10 meters thick, and it has a resistivity of 20 ohm meters. This will give you a chance to go back and make some of those conversions. How do we convert a resistivity into a conductivity? And then we have an uncontaminated aquifer here with a resistivity of 100 ohm meters. And beneath all that we have a layer of silt with a resistivity of 66.7 ohm meters. So this is a question you should be able to answer. Remember how we do it. We take the reciprocal of the resistivity, so we get 0.05 in this case, multiply it times 1,000. That gives us 50. So we have 50 millisiemens per meter or millimos per meter. And you would just do the same thing with each of these resistivities. But this is the basic model. We've got a transect across the area, and we're going to be looking at the terrain, the apparent conductivities that we get. We'll have sets of data that include all 8 measurements, and we'll be looking at those sets of data, modeling them in order to determine whether this aquifer might be contaminated, and if so, what's the extent of the contamination. We'll be plotting our data on a simple plot like this, and again, we're incorporating this geological background information. This is always something that you never want to miss. You want to use every piece of hard data that you can get, and that could include the geophysical log here, could include the observations from several water wells that have been drilled in the area and compiled by the geologist, telling us that this near surface clay is relatively constant in thickness across the area with a thickness of about 10 meters, and that the aquifer also is, we're making the problem, admittedly we're making the problem simple. The aquifer also has a constant thickness through this area of about 20 meters, and down to that underlying silt, at a depth of about 30 meters. So there's some background, there are some assumptions that we can use to constrain the models that we're going to develop. And again, just remember that the objective that we are pursuing in this modeling data acquisition exercise is to determine whether groundwater has been contaminated and the extent of that contamination. Sorry for that misspelling there. We'll go through this process a little bit, illustrate how we do it next time. See you then.